There's an important way of combining functions that turns out to be pretty important in differential equations and Laplace transforms applications, and it's a little hard to sort of describe why the formula is what it is. So rather than just writing down the formula, I'm going to do my best to sort of develop the formula with sort of some sort of intuitive reasoning for why the formula is what it is. So let's start with this scenario. Suppose that we start at time 0. We start dropping pebbles into a lake once every second. And of course, when you drop a pebble into a lake, it causes some waves. And what we're going to do is watch the resulting size of the wave at a spot near where we dropped the pebble in. And what we're going to ask is, at time n, so after n seconds, what is the resulting size of the wave? So that's going to be a function of how many seconds you waited. And we're going to try to build up a formula for this wave size function out of two other functions. So one is f of n, which is going to be the size of the pebble that we dropped in at time n. And so, of course, this is only going to be n for n greater than or equal to 0, since we start dropping in pebbles at time 0. And the other function is the size of the wave. So if you drop a pebble in, a unit-sized pebble in at time 0, this should be n equals 0, what is the size of the wave after you wait n seconds? So this one is a little tricky to wrap your mind around. So you can imagine if we drop a pebble in at time 0, right at time 0, the wave might be very large. A little after 1 second, the wave has maybe died down a little bit. And right, the longer you wait, the more this wave is going to die down. And the wave may never go away completely, but the size of the wave will get very, very small as time goes on. So that's what G is describing. It's if you have a unit-sized pebble at time 0, what is the resulting effect of that pebble later in time? So let's try to work out a formula for W. Well, to figure out the total wave size at time n, what we should do is look backwards in time at all of the pebbles that we dropped into the pond in the past and see what they add up to now. So we need to add up all of the previous times. And those times are going to be all times from 0 up to n. So we need to add up the current effect of the pebble that we dropped in at time I. That's time I. Okay, so it's going to be some sort of sum. So what is the current effect of the pebble at time I? Well, the pebble at time I, so the pebble at time I is, the size of that pebble is just f of I. Okay, because that's what f is. F is a function that tells you the size of the pebble you dropped in. And we need to multiply that by this, by the effect that this pebble has on the present. So what we need, it's G is the function that tells you the effect of that pebble in the present. But we have to be careful because what you put into G is the time since we dropped in this pebble, since time I. Right. Because right, the way that G is set up, G assumes that you're dropping a pebble in at time 0, and it tells you the effect n time units later. Well, this pebble in this scenario isn't being dropped in at time 0, it's being dropped in at time I. So G tells you the effect, right? What you put into G is how long ago you dropped in the pebble. So we have f of I times G of, so we just need to write down at time n, how long ago was time I? Well, that's n minus I. Okay, so here's our formula for our wave function. You see it sort of goes through all past times and figures out the present effect of the pebble that we dropped in at that past time. And it just adds up all of these effects. Okay, well this is a discrete situation, so our time values here are separate integers, and that's usually not how the functions we work with actually work. Usually the functions we work with are functions of a continuous variable, so let's see if we can work out a continuous version of this formula. So just to spoil the notational surprise, the notation that we usually use for the continuous version of this formula is f star g, and the name for this is f convolve g. That's how that's pronounced, or f star g, I guess, but the name for this operation is convolution. And it's basically exactly what you would guess for a continuous valued analog of this. So first of all, this is a function of a continuous variable, and we'll use t for our continuous variable. You can see we have some new variable inside of f, and instead of I, it's sort of traditional to use tau. So this right here is tau. It's a Greek t, sort of, times g of, and then inside of g we have our input time, which in the continuous case we're calling t, minus your new variable time, which remember we called tau, and then you add them up from 0 to your input time. But for a continuous situation, to add things up, you do an integral. So this is an integral from 0 up to our input time, which is t, d tau, right? This can't be an integral with respect to t when we already have t here. So tau is the variable, right? The sum is with respect to our new variable, and our new variable is tau. So this integral has to be with respect to tau. So this is a formula for the convolution of f and g. And it's really just a continuous version of the same sort of blending or adding up a history like the pebbles dropping into a pond example that we worked out a second ago.